Hello, everyone. Both the people who are here and most of them have been here with me throughout the semester. And those of you who are at home who hear me live for the first time this year. Well, you had 24 recordings of lectures from last year. I haven't changed very much. I just got 1 year older in the process. But that doesn't show on the recording. What we are going to do today is to solve exercises from one of the exam papers. We are going to do exercises from the recap exam from last year. Of course, none of you will go to the recap exam this year, so that's going to be your only chance to do a recap exam. As I was telling your colleagues, unfortunately, we don't have the proper software to actually allow me to write as well as I possibly might want to do on this screen. I'll do my best. What I strongly encourage everyone to do is to solve the exercises by yourselves. The people in the room will solve the exercises in this exam paper together with me. So in fact, most of the things that I will write are actually suggestions from the people in the room. If you're watching this recording, resist the temptation at all costs of listening to the answers from your colleagues. Stop the recording, solve the exercise yourself, and then see what your colleagues will have done if they were you. Okay, so let me try this. Yep, it seems to work. But of course, I want a larger window. So let's try to get one. I said larger window. Let's hope this is large enough. And I will have to do this process every time for every page that I need. So please bear with me. It's not fun. Oh, it only goes in one direction. Or this is the largest size, whatever. Okay, so I said recap 2015. For those of you at home, you just open your PDF file that is available under other material. For those who are here, we are doing a first exercise that has to do with structural induction over lists. We've done quite a few exercises of this type. This one is specified as follows. We want to define a function called epos1, a bit like ice hot 1 for those in the know, that takes as input a list of natural numbers and returns a Boolean. Now, what Boolean should it return? It should return true if the input list contains a 1 at all even positions. What does this mean? It contains a 1 at the second position, fourth position, sixth position, and so on, provided those positions exist. So at all even positions in the list, you want to see a 1. If you see something which is not a 1 anywhere in an even position, you spit out false. Is it clear what we want to do? Yes, so let's do it. Okay, that's supposed to be a recursive function, and I need to fit it in this screen. Okay, so where do we start? From the empty list. epos1 of the empty list. Now, is it true for the empty list that all even positions contain a 1? Some people are saying no. Why? Is there an even position that does not contain a 1? Well, the empty list has no positions whatsoever. So can you find an even position that does not contain a 1? No, you can't. So all even positions, none, in fact, contain a 1. The easiest thing is to return, in fact, the only reasonable thing is to return true here. Every even position of the empty list contains a 1. And it's easy to show. You don't have to do anything because there are no even positions. Cool. Zero work. I'm not asking, is there some even position which has a 1? Well, in that case, we would be in trouble because there is none. All I'm asking is it true that every even position contains a 1? That's true trivially. Remember discrete maths 1. Every element of the empty set has any property in the world, simply because you cannot find a counterexample. There is no counterexample. Okay? Now, do you think it might be a good idea to have another base case? Only one element. So if the list is of the form natural number empty list, so this is a list with only one element, then again, there is no even position. So every even position contains a 1. True. Okay, now we have dealt with the base cases. Now we need to deal with lists that have 2 or more elements. Now, if a list has 2 or more elements, it's going to look like this. It has a first element, it has a second element, and then it's followed by a list. Okay? So now, what is it that should we return? Well, now we need to look at what? Okay, does n matter at all for the result? It's the first entry in the list. Does it matter whether it's 1, 35, 1 million, or 4? No, it doesn't. Does m matter? Well, because it's, yes, it does, as your colleagues here are saying, because it's the second entry in the list. So it's at an even position. So what it should be? It should be a 1. If it's not a 1, what is it that you can conclude? You return false. So let's do a little base case, sort of case analysis. I return false if m is not 1. Now, what if m is 1? If m is 1, we say, so far, so good. But how do we figure out whether we are happy, we return true or not? We use the power of recursion. Absolutely. We call epos 1 on what? On L. Absolutely. Because that's the first entry, that's the second entry, and if we remove those, then we can restart afresh to check whether the position 4, 6, 8, and so on in the original list contain a 1 or not. Those positions will then, after you remove the first 2 entries, will become the second, the fourth, the sixth, and so on. End of exercise. Solution. And like in the Eurovision, you get 5 points from the Italian jury. Okay? Now we can continue. Any questions about this exercise? You know, by now you can even program, I think, some machine learning application to do these exercises for you. Unfortunately, you wouldn't be able to take it at the exam. Okay, if you're happy with that, I think I have no way to generate a different screen but to kill this one. So this is your last chance to say anything or forever rest in peace. This exercise gets married in a second. Okay, he said yes. So let's do another exercise. You should expand, please. Expand. Yes. Okay. Okay. The second set of exercises has to do with automata and regular expressions. The language is always the same. It consists of all of the strings of A's and B's that end either with BA or BB. So that's the property. And with BA or BB. That's the property we want. The first exercise says, give me a DFA for this thing. And on the text, I said 5 states, just to put an upper bound. In fact, we can do it with 4. So let's do it with 4, shall we? I want a DFA for this language. All the strings of A's and B's that end with BA or BB. I start by, yes? Okay, the question is, if I say with 5 states it's okay to do fewer, sure it is. In fact, we are going to do it with 4, I think. Absolutely. I just want to put an upper bound so that you don't start using 184 states. People do incredible things during exams. And figuring out whether something that could be done with 4 or 5 states, well, whether a solution with 15 states is correct is a hell of a lot of work. So I don't want to do it for 200 people. Sorry. Okay, so let's start. Give me an A. So if an A comes along, what shall I do? Loop. Stay in the first state. Because I haven't seen, well, it sounds reasonable, because I haven't seen any of the BA or BB pattern yet. Okay, what if a B comes along? We go to a new state where I have seen the beginning of the potential finish pattern. Okay, so now I'm in the new state. What shall I do if I see a B? You go to a final state. Now, should this state be final, the one that I just reached? No, because otherwise I would have accepted the string B, which does not end with BA or BB. Excellent. So I should go somewhere else. And this should be an accept state because I've now seen a string that ends with BB. Now, if I'm in this state here, this one, where this is not a start state, it's just the state where I'm currently in, then I'll erase this pointer just to make you feel at home with data structures. Okay, now I'm in this state that I've been pointing to with this arrow here, and I see an A. Where should I go? I should go to an accept state, but should it be a new one or the same one that I just used? What do you think? New one. Now, let me remove this pointer. Sort of intuitively, this state here means that I've seen a string that ends with BB, whereas here, I've seen a string that ends with BA. That might be useful to decide what we do later on. So suppose that I'm in the top accept state, and I now see a B. Where should I go? Loop, because I still see a string that ends with BB. I saw BB before, now I've seen another B, still it ends with BB. Now, if I'm in the top state and I see an A, we just go down, as a colleague of yours here is suggesting. Why? Because now we've seen a string that ends with BA. The previous one ended with a B, BB in fact, but it ended with a B. Now we've seen an A, so the string ends with BA. Okay, now let's look at the bottom accept state. What happens if I see a B there? Okay, one of your colleagues is saying, I go to this state. That makes sense because now the string ends with AB, so it's not a good one. The only useful information that I have is that the last symbol was a B. The A before doesn't really matter. It just tells me you should not accept. Okay, so if instead I'm in the bottom accept state and I see an A, where shall I go? We go back to the beginning because now we haven't seen anything of the good final pattern. The A here screws up everything we had before. Excuse my French. I don't know why British people say excuse my French, but okay, bingo. And the Danish jury says 8 points to the colleagues who are here in the room. Okay, you already have 1.3 points. It's getting close. Any doubt with this? Well, if not, I need to open a new thing, so this means I need to kill this. I'll kill it. I've never killed so many people in my life or so many exercises in my life, but there's always a first time. Okay, so ding. There you are. We are not doing geometry here. Just giving, whoa. Hello. Oh yeah, what's this? I have a strong temptation of drawing comics here. But anyway, now the second part of this exercise was to give an NFA with 3 states that recognizes exactly the same language that we had before. So ends with, that's the pattern, ends with BA or BB. An NFA for this language with 3 states. Now, let me ask you, have we seen these NFAs before in this course? Yeah, because this is a B as the second symbol from the right. We've done zillions of exercises like this. So these were actually 6 free points. So let's do it. And now we are using the power of magic, so we even have oracles helping us. In this case, we have about 30 oracles in the audience that you can rely on. So how does this NFA work? It starts reading its input string until it decides it is seeing the last 2 symbols in the string, at which point it counts down. Okay? So how does this work? I see an A. What should I do? Loop. I see a B. What should I do? Okay, you use the power of magic. We just ask the oracle, is this the second symbol from the right? Is this B the second symbol from the right or not? If the oracle says, no, you still have more stuff to read, we loop. If the oracle says, yes, it's the second symbol from the right, we count down. Now I'm in the state that I've just reached by doing the B. What do I do? No matter what I read, I go where? I read the last symbol, so I want to accept. Okay, the question is, can't you loop and make the second state an accept state? Let's try. I guess you want ABs here. What do you say? So can you give an example of a string that this guy here accepts and that you shouldn't accept? Well, magic happened here. Good. Sorry? Ends with AB. So for instance, BAB gets accepted here. BAA gets accepted. BA gets accepted, which is good, but we just make it like this. So this wouldn't work, but this would work. This would work, and it follows the pattern that we have used many times. You twiddle your thumbs until the oracle tells you, now you're reading the second symbol from the right. At that point, you move to a new state from which basically you want to see another symbol, no matter what it is, in this case, and you accept. Remember, an NFA accepts an input string if it has a way of processing it that leads to an accept state. And to find the good way, if one exists, or a good way, if one exists, we ask the oracle. We've left him sleeping for a while, but now she comes. This is a female oracle. She's coming at the exam to help you. Any questions with this? And the British jury gives us 6 points. Okay, actually, we don't really need that much space to continue for the next exercise, because the next exercise says, please give me a regular expression for this language. So what would be a good regular expression for this language? I think I can fit in down there. And let's write it in blue. just for a change. Okay, you know, I mean, once you look at the NFA, you basically have the regular expression staring at you. Why? Because the first loop is, yeah, any amount of A's and B's. Huh? It's a star. So it's either A or B star. That's the loop in the initial state. Well, at some point we exit from the loop. What do we want to see to exit from the loop? A B. That was not a trick question. After I've seen the B, I'm actually in this state. Pointer. So what do you think I should write to complete the regular expression? A or B? Bingo. Yoo-hoo. Smiley, and you got 6 more points for that. We are edging perilously close to passing this with flying colors. Okay, any problem with that? And of course, there are lots of regular expressions you can write, but don't make them complicated, please. Once you have the NFA, you got the regular expression, pretty much. Okay? Any problem with this? If not, we kill it. Okay, let's kill it. Bing. Okay. As you can imagine, this is real fun. The follow-up question was about grammars, 5 points. And he basically said, well, not basically, it said, give me a context-free grammar that generates this language. Now, we've done tons of exercises to build grammars of this type. Okay, so this is a context-free grammar. So like any good, honest-to-God context-free grammar, it has a start variable. And from this start variable, you should be able to generate the shortest string in this language. What is the shortest string in this language? It's C. It's not the empty string. Why? Because, okay, you can take 0 A's, but then you should have a C followed by 0 repetitions of BA. But you have to have a C. You know, there is no N on top of the C, so this means thou shalt write a C in between the initial NAs and BA, BA, BA 2 N times. Okay, so this tells us where to start the recursive process of generating a string. Okay, so now suppose somebody gives me a string that I've already generated and that has this form. How can I make it longer So I have this string in my hands. How can I make it longer in such a way that it's still in the language? So this is something that recursively I have already generated from S, which I have written here. Now, how can I make it longer and still get a string which is in the language? I can increase the value of n, which means I add 1a here. And what should I add at the end if I add 1a at the front? I add BA, but is it enough to add one BA? I should add it twice, because now I have n plus 1 a's at the front. I want 2 times n plus 1 a's at the back. So for every a you add at the front, you need to add BA twice at the back. Do I need anything else? What do you say? Well, I know how to generate the shortest string in the language, C. And given a string which is in the language, I know how to generate another one from it, which is longer and is still in the language. I don't need anything else. And the French jury says, 5 points, 5 points. Yes. So the question is, doesn't this generate A, C, A, B, A? But that's okay. Oh, yeah, I remember that. Yeah, so there was an error in this thing. Absolutely, thank you. Which I corrected during the exam when people ask me this thing. Sorry, I mean, shit happens. Anyway, the formal definition is what you should look at. And I can assure you that there are no such errors in the exam that I delivered today. Don't ask me what it's about, though. Okay, we got 5 points. Or you got 5 points. Well, actually, this time perhaps it was mostly me, but it doesn't really matter. This is a team effort. Okay, let's move on to the next question, which has to do with cardinality of sets. This question comes in 2 sub-questions. Okay, let me tell you what it says. For each of these 2 sets, it doesn't say 2, but I say it now, determine whether it's countably infinite or uncountable. For each countably infinite set, give a bijection between the positive integers and that set. Justify your answers carefully. Okay, so let's look at the first one. The set of real numbers between 0 and 1, union the set of real numbers between 2 and 3. Is this countable or uncountable? Uncountable. Why? Absolutely. Christian here is telling us, we know from the course that this subset here is uncountable. from the course. The whole set is bigger, or is at least as big, so it cannot be countable. Because if they were countable, then also the subset, the set of real numbers between 0 and 1, would also be countable. But it isn't. We know that. So end of answer. 5 points from the Greek jury. You know, this was not a trick question. Okay, just since you're so good, let me ask you a related question. Suppose I only gave you the interval 2, 3 of the real line, the set of real numbers between 2 and 3. Is this countable or uncountable? Uncountable, of course. Can you give a bijection between these two sets? Yep. Subtract 2. F of x is equal to x minus 2. Yeah? These maps 2 to 0, 3 to 1, and everything in between to the only corresponding number in between, 0 and 1. So this is a bijection. So if somebody, for instance, me, asks you to give a bijection between 0, 1, the interval 0, 1, and some other interval of the real numbers, there is typically in an exam situation a very simple function like this one. Just ask yourself, okay, how can I map the boundaries of this new interval to the boundaries of the interval 0, 1? If you can do that, well, it's going to work for everything in between too. Any question about this? If not, we move to the second part of exercise 4. Can we do this? Okay, forever rest in peace. And after that, we take a break. Well, unless you want to keep going, I'm happy to keep going. We just finished earlier. You just tell me. Okay, second part. Consider the set of natural numbers which are either of the form 3 to the power n, where n is greater or equal to 0, union 7 to the power m, where m is greater or equal than 1. Is this set countable or uncountable? Countably infinite or uncountable? Countably infinite, says Birkir. For those of you who are at home, Birkir is one of the guys in the room. So I'm respecting his privacy right now. Okay? So in this case, we were asked to give a bijection between this set and the positive integers. So we want a bijection here, a function f, which is a bijection between these two. Well, let's do it pictorially first, and then just for as icing on the cake, we are going to actually give the definition of the function. Okay, so let's do it pictorially first. Let's write down an initial fragment of the positive integers. Now, What is this going to be mapped to? How do you suggest we do it? Okay, so I got a suggestion from Birkir again. So he says 1 could go to 3. Now, remember the good old interleaving method. We don't want to discriminate the sevens, the powers of 7. So we just write the first power of 7 here. Actually, just a second. This should be a 1 because 3 to the 0. That's allowed. Whereas for 7, we only allow 7 and more. Okay, so now I don't want to discriminate the powers of 3. So I write a 3 here. That's 3 to the 1. That's 7 to the 1. Then I write the next power of 7. Then I write the next power of 3. And then if there was a 6 here, I would write the next power of 7. And I would keep going. Okay, so that would be already kind of good enough for me. But if you really want to make me super happy, you write the definition of the function, which you can actually read off from the picture straight away. Why? Suppose I give you as input an odd number. Well, the odd numbers go to powers of 3. And what is the pattern? One is 2 times 0 plus 1. 3 is 2 times 1 plus 1. 5 is 2 times 2 plus 1. Okay, but you don't need to do it because I've been kind enough to write it that way. So actually, this guy goes to 3 to the power of n. You can see it. 0 is 2 times 0 plus 1. 1 is 2 times, sorry, what am I saying? 1 is, this is a 3, 2 times 1 plus 1. 5 is 2 times 2 plus 1. And you can see that 1 goes to 3 to the 0. 3 goes to 3 to the 1. And 5 goes to 3 to the 2nd. And keeps going. If instead we have an even number, where n is greater than or equal to 1, where does this go to? 7 to the power of n. Two is 2 times 1, it goes to 7 to the first. 4 is 2 times 2, it goes to 7 to the square. 6 is 2 times 3, it goes to 7 to the 3. And it keeps going. So basically, once you have the picture, whoops, you can read off the function and be happy and get your 5 points according to the Croatian jury. Let's go to the Balkans. Any doubt about this? So this was question number 4. If there are no questions, I'll kill this off and ask you, do you want a break or shall we continue? Break. Okay, so we'll resume in 5 minutes.